Cool. So since maybe about 40 minutes we have, so what I'll do is the following. So maybe I'll try to explain in practice how you can understand and appreciate circuits better, right? So let's say you are given a circuit like this. Okay. So first let me draw the circuit. This is a small signal input and this is small signal Vout. Okay. So has anyone seen this circuit before? Hope not. Huh? Will I give it? Okay. Yeah. Oh, you solved assignment. That's good. Huh? So anyways, let's say you're given a circuit like this, right? I mean, you encounter this, or let us say you're in a company and in some design you encounter a circuit like this. So the point is how you go about understanding and appreciating the circuit better, right? Just wanted to talk about it. So the typical procedure is people just go with full-blown analysis to see what's happening, but instead I would recommend to take a 4-step approach. The first step is try to get a feel for what the circuit is actually doing. Try to understand the core functionality of the circuit, right? So I will say first you intuit. I mean, it's okay if you don't take notes. It's a general, talk. We'll discuss about the circuits. Anyways, lecture is uploaded, right? So by intuit, what I mean is the following: get a feel for what's happening in the circuit. So ignore all non-idealities in the circuit, and then see what's the basic functionality. So here, for example, I'll ignore R naughts of all transistors. Okay, and I'll even assume the GMs of the transistors are very large. Let's say it's infinity. If let us say GM of this transistor is infinity, what can you say if GM is infinity? What can you say about VGS? I mean, what is the small signal drain current in a transistor? GM VGS. I know the circuit is all fine, so currents are finite. If current has to be finite, GM is infinity, VGS must be. If VGS for this transistor is 0, what is my small signal Vout? So at least you know what is the functionality. So what is the functionality now? This is basically acting like a voltage buffer. That's all. So at least you know what is the circuit doing now. So now what I will suggest is think of any other circuit that you already know that can do a similar job. Do you know any other circuit that already does a similar job? What is it? Okay, common drain. So let's draw this. So this is your common drain structure. So here also, ideally my Vout is Vi. Then what should be the question you should be asking now? Yeah, I mean, if I already have a candidate who's doing some job, why will I go and hire someone else who seems to be doing a similar job? Right? Makes sense? And to understand this, we have to do some analysis. So second step is where you try to analyze. And I mean, this will not be a blind analysis, right? Because we clearly know what the circuit is actually doing, right? If you started off blindly without knowing anything, you will get some equations, but you will never know if it is correct or wrong. You might get a big equation at the output, but you will never know if it's correct or wrong. But now at least I know what I can expect from the circuit. Okay, so let's try to analyze and see what's happening here, right? And again, let's do small signal calculations. So help me because I don't exactly remember all results. So for small signals, I'll open the current source. So let's try to find the short circuit GM and RO. That is easier. So I'll find the short circuit GM. I'll short the output here, and I'm trying to find the current here. Okay, and remember, for small signals, a transistor acts like a what? Voltage controlled current source. So what is the current that will be pumped in by the transistor? GM times Vi. So let me mark it here. This is GM times Vi, and you also have the R naught of the transistor. Okay, I have not labeled the transistors. Let's all keep it GM R naught. It's okay. Now what can you say about the current flowing here? That's a gate. No current flows. So which means what can you say about this current and this current? They should be same. So which means the current flowing up, what is the value? That is also GMVA. Okay. Oops. Okay. This is also GMVA. So I have current GMVA coming, it is completely flowing through R0. So do you think any current of this goes to the output? Right? So this current basically circulates within R0. Done? So which means to find the short circuit current, what current I should be finding now? Current from the bottom there. To find the small signal current from the bottom transistor, what should I find first? The gate voltage of the transistor. So let me call it, maybe I'll use a different color, let me call it VG2 or VG something. Okay. And look at this, I have voltage applied at the gate. My source is grounded. I am taking the output from the drain. What should be the voltage here? What configuration does it remind you of? Common? I mean, why is it not here? Input is applied at the gate. My source is grounded. Where am I taking the output from? Drain. What configuration? So what should be my VG here? Minus GM R0 times. I mean, if it's not clear, I mean, it is not that difficult. The current flowing up is how much? GMVI. So which means the current flowing down is how much? Minus GMVI. This potential is grounded. So voltage is minus GM R0 times V. So let's quickly write. So this is basically minus GM R0 times VI. So what is the small signal current now? I mean GM times this gate voltage. So that's going to be GM times GM R0 times VA. Now do I, oh sorry, thank you, minus, yeah, very good, yeah, thanks. Now do you think R0 of this transistor will play a role? Why? Yeah, R0 is connected from drain to source. Both drain and source are small signal ground. That's basically out of the picture. So what is my total short circuit current now? Minus or plus? Plus GM? Yeah, GM square times R0. So what is my short circuit GM now? So it is of the order of GM square times. Okay, again, just see how the calculation is being done. We are not resorting to KCL. We are basically trying to use the results that we already know, looking at the circuit, tracing the current parts, voltages, and writing the result. Okay. And again, this is something you will get only with practice. So okay, this is short circuit GM for this guy, our plain old common drain. So if I find the short circuit current, I short circuit this. What is the short circuit GM here? Short circuit GM will be the GM of the transistor. Right? So okay, this is a short circuit GM. What should I find next? R out. So let's do that. So how will I find R out? Apply a test voltage and find the test current. Again, same old. And when I'm doing that, what will I do to VI? I'll make it down because I don't want this fellow to contribute to any current. So let us say I apply a test voltage here and try to find the test current. This is I test. So what do you think is the small signal current by the control source? GM VGS, what is the value here? Minus GM times. Once again, current here is 0. So where will this current flow to? It will basically circulate within R0 itself. Right? So which means if I say, if I mark the current this way, or maybe it's okay, let it be like this. GM times R, sorry, this is GM times VT. So which means the test current is contributed not by this transistor but by this fellow. So again I have to find the current here. So for that, what should I find first? This gate voltage VG. And can you help me find VG? What do you think VG is? VGD, what? VG plus? Yeah, how are you saying that? Yeah, I mean, what is the current flowing through the resistor R0 in this direction? Plus GMVT. So let me erase this actually, or let it be there. So what I'm saying is this current is flowing like this, minus GMVT. So which means the current flowing from top to bottom is plus GMVT. So which means the potential difference across R0 is GMVT times R0. This potential is at VT. So the VG will be at VT plus, right? If this was 0, you will say current times R. This is at VT. So this potential will be this voltage plus the IR drop across the resistor. Okay. So this is going to be so GM R0 times VT. So approximately what is it? IR VT plus GM R0 VT. So if I have to approximate as one term, yeah, GM R0 times VT. So this voltage is GM R0 VT. What is the current then? Oops, sorry. That's again same GM square times. So what is the test current now? Again, remember you also have an R0 here. So the test current will be this GM VGS current, which is basically GM square R0 VT plus the current flowing through R0, which is VT by R0. But I mean, we'll assume that R0 is large and this current should be much larger, that we can ignore this. Okay. So what is my R out approximately then? I mean, I'll basically ignore this term. So what is my R out? GM square R0 to 1 by GM square R0. I mean, yeah. Okay, so this is with this fellow. What about our poor common drain? What is the output resistance here? That's 1 by GM. So here my R out is, again, it's all approximate numbers, 1 by GM. So now we have all the results. Let's stare at them. If I find the small signal gain, approximately GM times R out is 1. Here also it is 1. So what is the main difference here? So can I say both are same, or is there something different in this? R out is? Yeah. So is it good or bad? Why? Yeah. We remember the functionality already we know. What is the functionality of both the circuits? For voltage buffer, how do you want the output resistance to be small or large? You want an output resistance that is as small as possible. So which of them is better? This fancy looking circuit is better. So at least now we know from our analysis that this circuit is better. It's a better voltage buffer because the output resistance is small. So what I'm saying is the analysis we did is not a blind analysis. It was basically a calculated and a measured analysis to understand this circuit better. So now from our intuition we found this is going to be a buffer, and from this analysis we figured out that this is a better voltage buffer than my simple source follower, in the sense that the output resistance is much smaller. Now a good engineer will stop here, but if you want to be a better engineer, I would say you take the third step. That is, you try to see if you can derive the circuit from scratch. Right? That is, see, I already know what is this fellow buying me compared to this guy, and what is the additional feature I am getting here? Output resistance is smaller. So you try to see, let us say I start with this common drain. Is there something I can do to make common drain to reduce the output resistance? And in that process, can I derive the circuit? The logic clear? That's how we should try to do, and let's try that, right? So let's take the same common drain. I am looking at the output resistance, so the input is shorted. Typically the drain is also small signal ground. Let's do it. So I am trying to find the output resistance, so I am applying a test voltage here and finding the test current. As of now in this circuit, my test current is how much? How much will be the test current here? Gm times Vt. We'll ignore R0 because Gm is much smaller than 1 by R0. Sorry, yeah, Gm is much greater than 1 by R0. So, but I want to have a smaller output resistance, which means, do you think this test current here should be larger than this or smaller than this? My output resistance is Vtest by Itest. I want to reduce my output resistance. So, do I want this Itest to be smaller than this value or larger than this value? So, which means in addition to this, I already have a current flowing. Let us say I also want to add a larger current along with this. And we already know the output resistance is of the order of Gm square R0. So, I will try to add a current which is of that same. If I can add a current of this value, my output resistance will be 1 by Gm square R0. Correct? And that's the output resistance you had here. So now I have to, Itest will have an additional component of this value. Now how many paths this current can flow from here? How many directions it can take once it comes here? It can go up or both. Right? So again, now you see you can have a case where you can push in that extra current in the upside or in the downside or both. In our circuit, where do you think that extra current is flowing? Up or down? Down. In our new circuit, the extra current is basically flowing down because of this value. Correct? So let's try to do that. So our goal is now try to add an additional current here. And what should be the value of the current? Gm square R0 times Vtest. So in principle, if I go and put a current source of exactly the same value, you are set. But of course, this current is not a constant current because it depends on the voltage. So I cannot have a ideal current source or a constant current source. What kind of current source I should have? Voltage control. And how do you make a voltage controlled current source? MOSFET. Transistor for small signals is a VCCS. So I'll replace this with a MOSFET. So I'll put an NMOS. Right? And what should this gate be connected to? I want to get a current of this value, correct? So what should the gate potential be so that I get this current? It should be Gm R0 times Vtest. Then the current flowing will be this voltage times Gm. That will be Gm square R0 Vtest. Okay, so now that begs the question. I have Vtest here. So which means I should do something to generate Gm R0 Vtest and then I connect it here. Right? And in this particular circuit, what is done is the following. See, you already have Vtest applied to the source of the transistor. I have a case like this. My gate is small signal ground. I am applying Vtest here. Is there some point I can tap the output from so that I get an amplified Vtest? Right. And what kind of configuration is this? Common gate. Gate is common. Remember, a common gate also provides voltage amplification. Right? If I apply some Vtest here, I get Gm R0 times Vtest here. So which means I should no longer be connecting this to small signal ground. I'll have it like this. So which means here I know I'll be getting roughly Gm R0 times Vtest. I mean, in fact, we calculated also, right? I mean, yeah. So I want this, I have this. What do you do? Yeah. You have your friend has pizza, you want pizza, you take it from your friend. Right? Same thing. So I'll go and connect. And that's all. So of course this is now let's beautify the circuit. So this is my actual circuit for small signals. So I'll apply the input here. Small signal output is taken here. And remember, this is the small signal picture. For small signal, I should have an open circuit. So what should I put here in the actual circuit? A current source. Simple. So this is one way in which you can actually derive the circuit. Right? And so we saw that this transistor, I mean this structure has a small signal output resistance than your simplistic source follower. Right. Now it turns out even at large signal picture there is an advantage here. So let me explain that. So let us say here I am going to connect my load. Okay, so this is my capacitor and I connect a load here. Now my source will be approximately at Vi, roughly. So the load current is approximately Vi by RL. So this is the signal current. This is not the DC current because I have blocked the DC. The signal current is Vi by RL. So if let us say the DC bias current is I0, what do you think is the total current flowing through the transistor? I0 plus, is that clear? I have a DC current I0, I have a signal current flowing through the load Vi by RL, so total current is this much. Now of course if my Vi is very small, you can this current is approximately I0, you're okay. But let us say my Vi starts to swing a lot, which means this current will change along with my input. If my total current in the transistor changes, it is as though my operating point is also changing a lot. So which means my GM is no longer a constant, it is going to keep changing with my input. Is that clear? So what I am saying is GM is not a constant, it is basically a function of input, so I will write it as GM times V, GM of V. So which means if you generate a current which is GM times VGS, do you think this term will be a linear term or a non-linear term? I mean this itself is a function of Vi, we are multiplying that with Vi, this will be non-linear. So basically this will be more non-linear. That happens if your Vi keeps swinging a lot. But let's look at this fellow. So here also let's do the same thing. I'll connect a load with a capacitor. So I have the load current flowing here. Now if I call this current as I0, what can you say about the current flowing in the transistor here? So which means who is providing the load current? I mean you see that the current here is constant I0 irrespective of the load current. So what path the load current has to flow to? This fellow, right? So load current will essentially be provided by this guy. Correct? So here you see that the main transistor here, it is biased at a fixed current I0 even though my load current changes. So this is basically better in that aspect compared to your simple source follower. Is that clear? Now I will say this is a second analysis you did and found that with respect to large signal picture, this is better compared to this. Why? What is the reason? The current is, yeah, not just operating, but total current to the transistor is constant, whereas here it changes with my input and the load. So now again you can try the following. Let's start with this source follower and see if we can make changes to this circuit so that I can keep the current in the transistor to be constant irrespective of the signal voltage or the load current. So let's try that. So again I will start with the source follower. Let me erase this. So remember, if I had the bias current here, then I will have some load current. I will call it IL. So which means the current flowing here is going to be I0 plus IL, and that's a problem. Correct? So which means now I cannot have this transistor providing the load current. I should provide some other path for the load current to flow, and that path, as we saw, has to be at the bottom. So which means in principle, let us say I put a current source here, some value Ix. Now what is the current through the transistor now? Ix plus IL. And how do you want this Ix plus IL to be? want this to be fixed. So let us say this must be equal to some constant current I0. See, now let us say you exactly know what is the load current. You can put a fixed current of Ix so that sum of these two is constant. Of course, that is not practical because the load current will keep changing. So once again, this cannot be a fixed current source. What kind of current source it should be? Variable current source. And how will the current be controlled? Through voltage. So what will I put here? Same thing. Maybe I'll use the same yellow. So I want to make sure the current here is Ix, and I'll have to change the current Ix so that sum of this Ix and IL is constant. So which means to change the current Ix, what should I be changing? The gate voltage of the transistor. And remember, now my goal is to keep Ix plus IL to be equal to I0. So in words, what will you do? I mean, you know that I have to keep Ix plus IL to be a constant I0, right? And to keep the current constant, what will you be changing? Gate voltage of each transistor? This fellow. So what might be the approach you take now? Now I have Ix plus IL. I want to make it equal to I0. What will be the first step? In English you tell me, right? I have a current Ix plus IL, right? I can measure the current here. I want to keep it equal to I0. What will be the first step in English? Let's not fix it. I mean, I have some quantity. I want to keep it equal to other quantity. What is the first thing I will do? I'll first check if they are equal in the first place. I'll basically compare the currents. And in mathematics, what is comparison? I'll basically have to generate, let us say I0 minus something like this, correct? And let us say I have a reference bias current I0. How will I subtract the currents now? I have current I0 flowing here, I have Ix plus IL flowing here. So what will I do? You basically do this. So which means a difference current flows into that parasitic capacitor here. So if let us say I0 is greater than Ix plus IL. So which means what should you be increasing Ix or reducing Ix? I should be increasing Ix. So I would say must increase Ix. So then what can you say about this voltage if I call this VB? That should also increase. And if I0 is greater than Ix plus IL, what do you think will happen to this voltage Vx? I am pushing in more current than the current that is being pulled out. So this voltage will, so this voltage is increasing, you want this to increase. So once again the same thing, you go on. So again, this is another way in which you can arrive at the same circuit. So that's what you should try to do, right? Because you analyze and see what the circuit is doing, and once you find a new feature of the circuit, you see how you can derive that same circuit from scratch. I mean, the nice thing is you already have the solution. It's like I'm saying prove that 1 is equal to 1. You already know finally 1 is equal to 1. I just have to figure out in between way. Correct? And I mean, this is something I always recommend to do, because if you are able to derive the circuit from scratch, right, then you will get a better understanding of the circuit. See, for example, you might have followed some line of thought in arriving at this circuit, for example, but the original inventor or the original designer might have had a different line of thought to get to the same circuit. If so, now you have gotten a new understanding or a new perspective of the same circuit, right? And that is very important for taking the fourth step, which is where I will call you innovate, where you try to come up with new circuits that does the same job with the same features, right? And in fact, a couple of days a student had asked me, in practice, how does someone come up with new ideas or new circuits? And my response is usually this: anytime you read a paper or come across a new idea, You understand that, then you try to reverse engineer that idea. You see, starting from scratch, how you could have arrived at the same idea in the first place, right? Because the moment you do that, you will get a different understanding of this problem solving process. Then you can take a different approach. Say, let us say for getting to that final idea, from point A you have to go to point B. Maybe there may be multiple ways to go from point A to point B. That particular idea you saw is doing it in one way. Maybe you can do it in a different way. See, let's take this example, right? Here, right? Here as we see, we had a case where I had V test here. I want to get GM R0 times V test. We did by doing this, but maybe you can do something else by doing something and connecting here. That gives a different circuit. Or even to start with, right? See, we saw that we have to add a large current here, and we saw the large current can be added in the up direction or the down direction. Or both. We decided to do only down. So if you actually do it in the up direction, you will get a different circuit. And in fact, that is also circuit that is already known. So I'll just show that. So again, the idea is same. I want to add a current. The extra current should be of the order of GM square R0 times V test. And I want to add the current in the top side. Okay. This should be GM square. Now again, this cannot be a fixed current source because it depends on V test. It is a voltage controlled current source. So remember, typically this is going to be supply. So because it is going up, so we'll use an NMOS transistor or a PMOS transistor? PMOS. So basically I'll replace it with, let us say, a PMOS transistor, and the gate voltage must be the same, GM R0 times V test. Once again, you can do the same thought process. If this voltage is V test, if I tap from the drain, I get GM R0 V test. So you can actually go and connect this. Right? This will give a different circuit, right? And if you have to sketch the full thing, this is only for small signals, where this is Vi, this is Vout. For small signals, this is open. So what will I put here in the actual circuit? You have to put a current source so that this biased. Now we'll get a new circuit, right? And I always say, anytime you come up with some new circuit, first thing is to give it a good name. If you had come up with the circuit, you could have given it your name, but unfortunately no. So let me copy that also. Oops. Yeah, so this fellow is called as flip voltage follower. And this is called as super source follower. I mean, don't ask me why this is called super and why this is not called super. Again, if you had come up with if you had come up with this on your own, you could have given your name. In fact, if someone comes up with some good circuit in the future, you can consider naming it as E610 IITK so that everyone will know. See, another way to think about it is this, right? See, I know already that with respect to small signals, is there any difference between using an NMOS transistor and a PMOS transistor? Small signal equivalent is both same for the both. So basically what I did here, I had an NMOS transistor. So I could as well have done it using a PMOS transistor, which is what I'm doing. That's other way to come up with the new circuit. Right? And yeah, we already know for small signals both are going to be same. So there will be a difference only in the large signal. And if you want to know the difference, so let me show this once. So let us say this is my load RL, this is my load current IL, and I know this was my current IX, this was IL plus IX, which is set equal to I0, correct? Now let us say my input voltage is, small signal voltage is negative, less than 0. So which means, what can you say about the load current? Will it be positive or negative? Negative. I mean, this voltage is approximately Vi. correct? So this is Vi by RL. If Vi is negative, this current is also negative. If the current is negative, do you think the current is flowing from left to right or right to left? It is flowing from right to left, correct? And I also know my IL plus Ix must be equal to constant I0. So what I am saying is now my IL is negative, which means this portion is becoming more negative. To keep the sum to be constant, what should happen to Ix? Ix will keep increasing, right? So I will say Ix keeps increasing. So which means if Vi becomes more and more negative, this current becomes more and more negative, and Ix will keep increasing accordingly to keep the current I0. No issues. But let us say Vi is greater than 0. Then how will the current flow? From right to left or left to right? Current will flow like this. And I know IL is greater than 0. So if I keep increasing Vi, this current will keep increasing. So what should happen to Ix? Now Ix will keep reducing. Now do you think Ix can keep reducing, without any limits, or is there a limit? What is the minimum Ix can go to? And what is the minimum current you can have? Huh? I mean, this is the total current in the transistor. The total current in the transistor, what is the minimum value it can take? 0. Right? That's all. See, this will keep reducing. And once it hits 0, that's it. Correct? So, which means, what is the max? If this becomes 0, what is the maximum load current I can have? And this is happening only in the positive side. On the negative side, you don't have that problem, because if Vi is reducing, Ix has to keep increasing. Yeah, that will happily do. But on the other end is where you have problem that Ix is reducing and the minimum it can take is 0. So this fellow has limitations with respect to positive IL. Similarly, if you work out, this fellow will have limitations with respect to negative. So you have one that is working nice for positive, one working nice for negative. What do? You combine the two, and that's what people do sometimes. Or I mean, that's also another thing people do. And that is another way to come up with new ideas. You learn about some idea in one place, second idea in another place. Now you think, what if I combine the two? It might work. Okay, that's other way to come up with new ideas, right? So which means what I have to do, add a PMOS transistor, something like this. So if I give the circuit, directly it looks ultra complicated with fancy connections here and there. But if you break it down, this becomes simple. So the bottom line, I just gave a general gyan. Not just in circuit, right? Anything that you are doing, you first try to intuit and analyze. That is something you should definitely do, right? And once you do it, you try to derive the circuit or the idea from scratch yourself, right? And if you are doing it, that's very good. That will help you in doing the last step, which is what research students, MS PhD students, you should be trying to do. Try to innovate. And for you to do this part, you should be doing good in these 3 parts. Okay. And I'm not saying this is the only way in which you come up with new ideas. That's not the right thing. This is one way in which you can come up with new ideas. Okay. So anyways, I'll stop here. We'll continue.